But we're talking about hundreds of millions of times the mass of the sun. But it's a black hole, so it's small for that much mass.
Wow.
The sun goes around a black hole in the constellation Sagittarius at the center of the Milky Way galaxy.
However, the mass in question is hundreds of millions of times that of the sun. However, given its mass, it is small, a black hole. In the Milky Way galaxy's core, in the constellation Sagittarius, the sun revolves around a black hole. Researchers have found an astounding finding at the core of these mysterious cosmic monsters. They have discovered something horrifying and mind-blowing within a black hole, appending what we previously believed to be true about these celestial marvels. Get ready as we reveal the incredible mysteries that lie within the enigmatic center of a black hole. Do you want to learn more about it? Now let's get started. What a fascinating thing black holes are. Albert Einstein, a renowned physicist, said that even traveling at the speed of light would not be able to escape the strong surface gravity of his day due to his theory of general relativity. You are stuck here forever. Unlike pushing and pulling or magnetism, gravity is the outcome of mass and energy-driven objects curving or bending space and time. Envision possessing a gigantic object in space, akin to a star. The fabric of space and time surrounding it has a significant depression or bend because to its immense bulk and activity. We refer to this curve in space and time as the gravitational field. The object's gravitational field is greater and the dent it makes is deeper the more massive and energetic the item is. Now that theory is in place, let's discuss black holes. With unbelievable quantities of mass and energy condensed into such a small area, they are among the universe's most extreme things. Its massive mass causes its gravitational field to become extremely strong. The fabric of space and time is severely damaged by the powerful, deep dents caused by this high gravity. This is where things get very weird. An event horizon is formed when the gravitational attraction of a black hole gets so intense that it approaches the black hole. The event horizon is just space passing through without obstruction. It is not a wall. A point of no return or invisible limit is what it feels like to cross the event horizon. Anything that crosses this line, be it light or an unfortunate spacecraft, can never again escape the black hole's clutches. It appears as though everything, even light, which is typically the fastest object in the cosmos, is contained inside the black hole by an unseen force field. To put into perspective just how amazing this is, picture yourself holding a flashlight. The laser beams move at a speed of over 300,000 kilometers per second. The speed you would need to escape a black hole, however, would be much quicker than the speed of light if you were within one. As far as we now understand physics, that is not feasible. Thus, light that falls into a black hole becomes stuck there forever and cannot escape. Light from a greater distance is curved around it. Thus, we must not overlook the event horizon, a mysterious boundary, when discussing black holes. It resembles a point beyond which anything courageous or unfortunate enough to cross it cannot return. Something can never return once it passes through that point and plunges into a black hole. The event horizon is a mathematical term that indicates the point at which we can no longer perceive what is happening. It is not something you can physically touch or see. One may question what the size of this event horizon is. All of this is dependent upon the black hole's mass, or the Schwarzschild radius. A black hole's event horizon will enlarge with increasing mass. The Schwarzschild radius is the value that scientists have determined to be the event horizon's radius. It was discovered in 1916 by an astronomer by the name of Carl Schwarzschild. The Schwarzschild radius is calculated by dividing the black hole's mass by a formula that takes into account both the speed of light and the gravitational constant. For instance, the event horizon of a black hole with a mass 10 times that of the Sun would be around 30 kilometers in radius. An entity called the singularity is located in the center of a black hole. No matter how enormous, everything of the black hole's mass and energy are crushed and squished into an indefinitely small, dense point at its core. This point is known as the singularity. It resembles a cosmic heavyweight with amazing curve and gravity. It's actually rather amazing that the singularity has limitless curvature and unlimited gravity. The problem lies in the fact that, while attempting to explain what occurs at the singularity, our knowledge of physics begins to break down. We just aren't aware of what occurs there. We are left wondering why the rules that govern our cosmos seem to take a pause or go on vacation. researchers continue to go into this mysterious area in the hopes of learning the mysteries that lie at the center of black holes. Furthermore, how do black holes form? You know, everything begins with a huge star's life cycle. Deep within their cores, these stars undergo remarkable nuclear fusion events that drive them like celestial powerhouses. Think of these responses as an amazing culinary program. Fusion is a particular nuclear process that converts hydrogen into helium, which fuels the sun. When two hydrogen atoms are forced together, one helium atom is produced as the byproduct, where a huge quantity of energy is released as hydrogen atoms combine to generate helium atoms. Now, the star stays stable as long as it has enough hydrogen fuel to continue the fusion process. However, celebrities are avaricious and desire to prolong the fusion celebration. They become a little inventive when the hydrogen in their core runs out. They begin combining elements that are heavier, such as oxygen, carbon, and helium. Less energy is produced by each heavier element fusion process than by the preceding one. The star must burn hotter and work more to make up for this, increasing the heat in order to preserve its delicate equilibrium. Sadly, the voyage of every star must come to an end. The star approaches a point of no return when it is unable to combine additional elements. Something amazing is happening right now. A black hole is created when the star's core collapses due to its immense weight, like a beautiful implosion. The singularity, the center of the black hole, that we previously discussed is formed when the core collapses. Not even light can escape the strong gravitational attraction created by this singularity, which contains all of the star's mass and energy in a little amount of space. It has the effect of drawing everything into its gravitational pull like a cosmic vacuum cleaner. What happens to a star when its life is about to end relies on its mass, or, more accurately, on its size. Let's divide it into three outstanding weight groups. First up are stars with a mass less than 3 times that of the Sun. These stars are about to undergo a change. Rather than ending dramatically, they transform into an entity known as a white dwarf. It's as if the celebrity decides to gently step down. Inside is a compact ball of carbon and oxygen atoms that is still emitting light in the form of leftover heat. Now, prepare for an amazing show if the star has a mass of anywhere from 3 to 20 times that of the Sun. These stars explode with a tremendous supernova explosion. This star's core collapses dramatically in the middle of the explosion's mayhem. It turns into a neutron star, which is a very dense ball. Imagine packing a small sphere with a radius of just around 10 kilometers, containing up to double the mass of our Sun. Now, actual heavyweight stars, those that are heavier than around 20 times the mass of the Sun, explode in a supernova similarly to their somewhat lighter siblings. But the fate of these massive stars' cores is different. Under the force of its own gravity, it falls, but it doesn't end there. Once more, a black hole is created when the gravity gets so strong that the center contracts to zero volume and infinite density. There are several varieties of black holes. We have black holes with stellar masses. These originate from huge stars that are getting close to the conclusion of their stellar journeys. They are usually a few times to several tens of times as massive as our reliable Sunday. In reality, both our galaxy and other galaxies throughout the expanse of space are home to a large number of stellar mass black holes. Let's now turn our attention to the gigantic supermassive black holes. The real giants of the black hole family are these enormous cosmic entities. Their masses are millions, if not billions, of times larger than the Sun's. Imagine them as the lords ruling over most massive galaxies, like the Milky Way, from their central position. These enormous black holes are believed to have originated in the early phases of the cosmos as a result of smaller black holes merging or vast gas and dust clouds collapsing. Their existence has a significant impact on how galaxies evolve, influencing how stars and planets that orbit them originate. Well, we have now encountered intermediate mass black holes, an uncommon kind. In terms of mass, these enigmatic entities fall in between stellar mass and supermassive forms. They are quite enigmatic and seldom seen, much like the middle offspring of the black hole family. Although their exact origin is still unknown, scientists believe that they might have arisen from the merger of stellar mass black holes in densely populated star clusters or from the collapse of extremely massive stars in the early cosmic periods. And then, there are the fascinating primeval black holes. These might be remnants from the first moments of the cosmos, created not long after the Big Bang. They are born because of variations in matter and energy densities in those early cosmic moments. There are many different sizes of primordial black holes, ranging from tiny ones with weights of only a few grams to gigantic ones thousands of times heavier. Then the Sun. Remember that although primordial black holes are an intriguing concept, they are still theoretical and have not been witnessed firsthand. Rotation is another fascinating feature of black holes. The Schwarzschild black holes are one example. These are the easy ones, the ones that don't spin. Consider them the group's cool, collected black holes. The Schwarzschild solution, a mathematical explanation found in Einstein's general theory of relativity, describes them. These black holes feature a unique point in the center known as the singularity and a lovely, spherical event horizon, which functions similarly to a border denoting the point of no return. It resembles a single dot with a powerful gravitational attraction. Similar to this, you will reach the center if you fall through a black hole's event horizon. Next, there exist Kerr black holes, which the general relativity Kerr solution describes. Their event horizon is flattening or becoming oblate due to their rotation. In a Kerr black hole, the singularity has a ring-like form. The ergosphere is created when a rotating Kerr black hole rotates. The area surrounding the black hole resembles a cosmic vortex as the spinning black hole drags space and time with it. Let us introduce you to the Kerr-Newman black holes. These are the rotating rock stars with a little something extra. They have an electric charge in addition to spinning. In general relativity, Kerr-Newman black holes are characterized by the Kerr-Newman solution. Their ring-shaped singularity and oblate event horizon are two features they have in common with Kerr black holes. But the electric charge gives their tail a new angle. The electric field somewhat distorts the event horizon and singularity. Ultramassive black holes have also been discovered by scientists. Extremely big black holes are amazing cosmic heavyweights. At almost a staggering 10 billion times the mass of our dependable Sun, it tops the scales. We are discussing a black hole with an unfathomably powerful gravitational attraction. Anything that approaches it too closely is going to go through a crazy roller coaster. How in the world did we find these cosmic monsters? An astute group of astronomers from Durham University in the United Kingdom accepted the challenge. They employed a state-of-the-art method known as gravitational lensing. It may sound elegant, but it's genuinely quite interesting. The amazing general theory of relativity developed by Albert Einstein states that large objects, like as galaxy clusters, have the ability to bend and warp the course of light. This gravitational lensing method allowed the researchers to identify the distinctive features of an ultramassive black hole. In my opinion, we may be witnessing the emergence of new laws of physics due to the massive black holes that we are studying. They saw the amazing light bending and magnifying that this cosmic heavyweight produced. In addition to proving the existence of ultramassive black holes, this important finding offered more evidence in favor of Einstein's general theory of relativity. The powerful Hubble Space Telescope was used to make this finding. Our daring researchers focused on the AEL 1201 galaxy cluster, which is located 2.7 billion light-years from Earth. This is where things start to get really interesting. Looking into space, they saw something strange, a massive arc of light around the cluster. But that arc was more than just a regular light display, it was the warped representation of a distant galaxy, stretched and smeared by the cluster's gravitational pull. And how, then, did they solve this cosmic riddle? They used the computing capacity of supercomputers, after all, to model the motion of light across the enormous cosmos. They were able to determine the mass and position of the object, causing the lensing effect by meticulously recreating the background galaxy's brightness and shape. And you know what they found? A supermassive black hole was discovered to be hiding in the center of one of the cluster's galaxies. The mass of this black hole was an incredible 30 billion times that of our own Sunday. That's among the biggest black holes in the cosmos that has ever been seen. Moreover, this amazing finding was the first instance of a black hole being identified through the use of gravitational lensing. The remarkable power of gravitational lensing is highlighted by this discovery. It's like having a cosmic magnifying glass that lets us view and learn about things that would otherwise be too faint or concealed to be directly detected. By using this method, there are a plethora of new opportunities to solve the riddles surrounding black holes and other unusual objects that may be hiding deep within space. Consequences: for example, if you observe gravitational lensing in action, you may utilize what you observe to calculate the mass of the lens. This brings up an incredible application of the gravitational lensing theory. It allows us to see the invisible. However, this extremely huge black hole throws a wrench into our understanding of how they formed and expanded in the early universe. You see, the conventional theory of how black holes form over time is called into question by its sheer magnitude, which is so very huge. It would have required an incredible rate of accretion to attain such a massive mass, 30 billion times that of our Sun, in just 13 billion years after the Big Bang. Imagine it as an accelerated feeding frenzy that draws matter in at a startling rate. Alternatively, it might have created via spectacular mergers in which it collided with other black holes in the universe. This finding provides new and fascinating opportunities to explore the cosmic processes that form these mysterious cosmic giants. Nevertheless, we have a unique chance to test Einstein's theory of relativity in harsh environments because to this extraordinary ultramassive black hole. Test: by examining these cosmic monsters that defy our comprehension of gravity, we may test if Einstein's hypothesis still holds true in the most extreme cosmic conditions. It is akin to carrying out an intergalactic investigation that explores the fundamental structure of space and time. Finally, this finding presents an enticing opportunity to investigate the characteristics and nature of dark matter. The bulk of the material in our universe is made up of dark matter, an enigmatic and unseen kind of substance. We can learn more about the distribution and impact of dark matter and its elusive nature by examining the behavior and interactions of ultramassive black holes such as this one. When mass, space, and time come together, gravitational lensing produces amazing visual illusions akin to a cosmic magic show. This is how it works: mass has a significant impact on the structure of space and time, causing it to twist or curve around itself, in accordance with Einstein's theory of relativity. Imagine it as a trampoline with a divot caused by mass. This warping causes objects passing close to follow bent pathways. Now, this cosmic phenomena also applies to light, which generally moves in straight lines. The gravitational warp catches up with light when it passes through enormous objects like galaxies or clusters of galaxies, causing it to follow curved pathways as well. Herein lies the significance of gravitational lensing. Consider that there is a light source in the backdrop, such as a star or a far-off galaxy. Its light encounters a large object along the way that serves as a cosmic lens as it makes its way across the cosmos towards us. The light from the background source is bent, magnified, or otherwise deformed by this enormous object due to its strong gravitational attraction, producing captivating effects. Gravitational lensing comes in a variety of forms, each with unique peculiarities. First, let us consider weak lensing. The forms and locations of faraway galaxies are subtly altered. It's like wearing slightly hazy glasses. It will need statistical analysis of several galaxies for scientists to find these alterations. Important information on the distribution and amount of dark matter in massive cosmic structures such as galaxy clusters may be obtained via weak lensing. It's similar to finding unseen cosmic fingerprints left by the enigmatic dark matter, and this brings us to an incredible application of gravitational lensing theory. It allows us to view the invisible. Let's go to stronger lensing now. This is analogous to a cosmic superpower that materializes when a huge item and a far-off source perfectly coincide. Multi-images, arcs, circles, or other distorted patterns of the background source whirling around the lensing item are examples of the mind-bending effects that may be produced by strong lensing. It resembles peering through a kaleidoscope of the cosmos. This strong phenomena not only magnifies and reveals hidden features of distant sources that would otherwise be too weak or tiny to view, but it also aids in the measurement of the mass and form of the lensing item. Then, there is a unique situation known as microlensing, which adds a hint of heavenly drama. When a smaller object, such as a planet or star, passes directly in front of a more distant star, microlensing occurs. The background star seems larger or brighter as it becomes lensed because the foreground object serves as a temporary magnifying lens. Microlensing is an interesting technique for identifying other rare cosmic wonders, such as black holes or neutron stars, as well as planets orbiting other stars. Scientists have targeted their advanced telescopes on a supermassive black hole located 800 million light-years distant, near the center of a galaxy, and they have discovered something startling inside a black hole for the first time ever. Black holes are notorious to eat everything that approaches them too closely, owing to their voracious appetites. Well, in this instance, something remarkable was brought about by the black hole's cosmic feast. Gas from the surrounding area was heated to extremely high temperatures, millions of degrees, when it plummeted into the black hole. Like a bright cosmic halo, this scorching hot plasma created a luminous corona surrounding the black hole. The crazy thing is that these X-ray flares, cosmic fireworks, produced by the superheated gas, didn't simply vanish into the cosmic abyss that is the black hole. Whoa, they did have a cosmic rebound after all. The X-ray flares were able to escape, but in an unusual way, the gas just behind the black hole reflected them. That's not all, though. These reflected X-ray bursts then encountered another cosmic barrier, the black hole's magnetic fields and mind-bending gravitational force, as if defying the rules of physics. That's all in this video. If you like the information, please hit like and subscribe to this channel. And be connected to this channel for more space information.